Alrighty. Do y'all need more lights off? Is it not dark enough? Yay, nay? Okay. You need it dark? Is that what you said? Oh, you hate dark. Okay. Day 8. Y'all remember at all what we were doing last time? Double integrals, right. So we had talked about, we had finished up 12.1, right? And we were moving into 12.2. I just briefly started talking about 12.2. And we have quite a bit of work to do today. So let's get right to it. We're going to look at trying to find double integrals over general regions now. 12.1, we are trying to find double integrals over rectangles. So our domain on the ground, right, was a rectangle. Take that, map those points into the function, then find the volume of the solid between the function and the xy plane, right? That was what we were doing. Now we have these other looking regions. So there's your rectangle. And now we have the type 1 region. So a type 1 region is a region where we use capital D to define the region instead of capital R. It's all of the x and y, so all of the ordered pairs, all the points, where your x is stuck between two constants, a and b, and your y is now stuck between two functions of x. So graphically, it looks like this. So your a and your b are here, your x's are between there, and then your y's are trapped between two functions. If we have a region that looks like that, we call it type 1. Now, if f is continuous on a type 1 region, then the double integral over that region D of a function of two variables with respect to that area is going to be the outer integral is the integral with respect to x, and the limits of integration are the constants. The inner integral will be with respect to y, and the limits of integration will actually be two functions. So previous to this, these were always constants, right? Now these could possibly be functions of x. And so we'll see how that's going to change the way things integrate. And then if we're trying to find the volume between two surfaces, so you have a surface F on top and a surface G on the bottom, then you can still do that over a type 1 region by using this formula right here. Just subtract the two volumes, right? So here's our first example. Okay, find the volume under z equals x plus 2y on the region bounded by y equals 2x squared and y equals 1 plus x squared. So the first thing we have to do when we're going to set up problems like this is figure out what our region looks like. And now I've already done it for you here, but that's something we would have to do on our own, and I'll go through the work for that in a second. But let's just take a look at it. We have basically two parabolas, right? Here's a parabola on top, here's a parabola on the bottom, and then there's a region that they enclose. That's going to be our D. Now, it's obvious it's not a rectangle, right? Does everyone agree that the x values are trapped between two constants, -1 and +1? And then our y values, they're trapped between two functions of x, the upper and lower parabolas. And now if we imagine that region on the ground in three-dimensional space, we have some surface above it, which in this case is a plane, and we're trying to find the volume of the solid below it, like that. Okay, everyone see that picture? That makes sense? Okay, now let's act like we didn't have that picture, and let's try and work through this problem. And the way I worked through this is pretty much what I would expect to see on a test. You need to draw the region, label everything. So I'm going to start out by writing out my function, z equals x plus 2y. The region is the one formed by the boundary of these two. So I'm going to start with the region. I'm going to draw a graph here. And now I need to draw these two. So these are parabolas. I would expect that you can graph these parabolas. But to do it quickly, let's draw this one. And we won't label them G1 or G2 yet. Let's draw them first. So to draw that first one, y equals 2x squared, I could just plug in some values of x. Like if I plug in 0, I get 0. Plug in 1, I get what? 2, right? Plug in negative 1, I also get 2. And so I know it does something like this, right? Now the other one, I'll do in black. If I plug in 0, I get 1. If I plug in 1, I get what? 2, so I'm here. And then if I plug in negative 1, I get 2 also. And that's a parabola that looks like this. Got it? So the region bounded by the two of them would be this region here. Whoa. Now, when you first do a drawing, you might have to take a moment to actually draw a better picture, right, if you wanted to. But we need to know, by looking at this, if it's type 1 or type 2. So how are you going to determine if it's type 1 or type 2? I'll zoom on it. Okay, so by looking at this, if I draw a little vertical line in here like this, okay, that little line segment, the y values are bounded between this curve and this curve, right? And those two curves are functions of x. If I try and draw a line segment the other way like this, horizontally, now my x's are bounded between two things, right? But here, isn't this curve the same curve as this curve? So it's not, my x's, if I looked at it this way, my x's would not be restricted between two different functions. It would be restricted between the same curve. So I wouldn't have a top and bottom function. They're the same curve. Does that make sense? So it would make more sense for us to look at it with a vertical limit being two functions. Is that clear for everyone? Now, if my two parabolas are going to be my restrictions on y, then I just need to figure out what my restrictions on x are, and they're between these two values here, right? So as x varies through, my y values are just stuck between the two graphs the whole time. Now, what are the x values that they're stuck between? Or what's my x value stuck between? Negative 1 and 1. Now, I could do that just by visually doing it, right? But what if it wasn't easy to do it visually? How could you determine 1 and negative 1? Set those two equal to each other. Set the two right here equal to each other. So if I did that, I would get 2x squared equals 1 plus x squared, right? Subtract x squared on both sides, I get x squared is 1. Take the square root, plus or minus, you get, those are your two x values where they intersect. So that's how you could get it if you couldn't see it, right? Okay, so I think now I need to label these graphs, these parabolas. One of them needs to be my G1, one of them needs to be my G2. So the G2 should be the one on top, the G1 should be the one on the bottom. So which is this one right here? G1 of x, right? And which one was that? 2x squared, right? And then my G2 will be this one. G2 of x is 1 plus x squared. Okay, now I'm going to give a representation of what that region is in terms of what are the boundaries or what are the restrictions on x and y. So I'm going to just list this out. My x here is bounded between negative 1 and 1, right? My y value is bounded between the two curves, 2x squared and 1 plus x squared, right? That describes my region D. And now I can go set up my double integral. It's a type 1 region, so the outer integral is going to be my restriction on x, which is -1 to 1. My inner integral will be my restrictions on y, which is from 2x to 1 plus x squared. And then what is it that's in my integrand? What's the thing that I'm integrating? The surface itself. Now the surface, back up here, right? I could have rewritten that f of xy equals x plus 2y instead of z. But this is my surface. That's the thing that goes in the integrand. So I put down here x plus 2y. And then I integrate with respect to what first? dy, right? So dy and then dx. This is the integral that we're going to evaluate now. The double integral. So let's work with that inner integral first. If you take the antiderivative of x plus 2y with respect to y, that means treating y as your variable, treating x like a constant, then what is the antiderivative of x? xy. And then plus the antiderivative of 2y with respect to y would be y squared. Now I need to evaluate that at the two limits of integration. And I don't know if you remember when we were doing rectangles, I told you that you might get into a habit of writing down what you're replacing. What is it that I'm going to replace here? The x or the y? The y, because I integrated with respect to y, right? So I'm going to put here, I'm going to replace y with 2x squared, and then I'm going to replace y with 1 plus x squared. Now remember, that's all sitting inside of this other integral that we'll do after we evaluate that. Pardon me? Yes, that's fine. Yep, you can go work that whole inner integral first, and then figure out what it is, and then come back and just put it in there. Some people work the inner integral on its own. Some people carry the notation the whole way. It just depends on your preference. So this is equal to this. Okay, so now what we would need to do is first plug in 1 plus x squared in for y. If I do that, I would get, what, x times 1 plus x squared, and then plus 1 plus x squared squared. So that's what I get when I plug in the upper limit of integration. And then I subtract from that what I get when I plug in the lower limit, right, for y. So what happens if I plug in 2x squared? I get 2x cubed, and then plus 2x squared, all of that squared, so 4x to the fourth. And then I'm going to figure out what that is, and then integrate that with respect to x. Now, how would you figure out what's in there? How about like distribution of x through here? Expand that polynomial out, right? Distribute your negative sign through, collect all like terms, and everything that you would have left would be just a big polynomial in x, wouldn't it? You could integrate a polynomial in x, term by term integration, power rule, right? And then plug in 1, plug in -1, you're done. Dot, 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 which means I'm not doing that. Yes? You're saying do the double integral. No, I think I understand what you're saying. What I'm assuming what you mean is if I have this, right, like that. Okay. that forget this one's here, right? And then look at that as your region, and look at the volume of everything above that from the surface down. You could do that, and then you could subtract from that everything above that surface down. Sure. Yeah. But it seems that would be two separate double integrals that you would have to do. They would still both be double integrals. The difference would be this is a type 1 region, okay, where your G2 is this, and your G1 is 0, the bottom, the x-axis. So y equals 0 would be your G1. So it wouldn't really, do you see what I'm saying there? Okay. All right, so let's look at this one. We have find the volume under z equals x squared plus y squared on the region bounded by y equals 2x and y equals x squared. So in an effort to save us some time, does everyone believe that they could graph the region? Yeah? You have a parabola, x squared, y equals x squared, and then you have a line, 2x. So you graph them. You figure out where they intersect each other by setting them equal to each other, and you'll get two solutions. You should get 0 and you should get 2. And then from here, you know what your upper and lower limits, or your upper G2 is and what G1 is, right? And then our restriction on x would be from 0 to 2. So let's just set up the double integral for this one. All right, is that fair? Just set it up. Okay, so I would have double, what's the restriction on x? What's the restriction on y? I should say it that way. 0 to 2 on x. And then y, it looked like the line was on top, right? So the line was 2x, and then the parabola was on the bottom, which was x squared. So I'll have 2x on the bottom, x squared on the top. So I'm going to go double integral 0 to 2, 2x to x squared. And then now the integrand is the surface, which was x squared plus y squared, dy dx. And then is it okay? Go ahead. What? Oh yeah, I wrote it backwards, so I apologize. Thank you. 2x x squared. I wrote it wrong here too. X squared was on the bottom. Please make sure you see that. X squared's on the bottom, 2x is on top. X squared's down here, 2x is up there. Now, do I need to go through the integration, or is the setup of it okay? How do y'all feel about that? You okay with me just setting it up? You integrate that with respect to y first, plug in x squared for y, and then 2x, subtract. You'll get a nice polynomial. Do you remember with rectangles we could switch the order of integration? Do you remember that? Can we do that with type 1 regions? No, you cannot. All right, you're forced to go with this order. Okay, so what about a type 2 region? So type 2 region looks like this. And to distinguish it from a type 1, I want to point out that if you were to try and come in here with a vertical line segment, right? Like let's say I had a vertical line segment right here, and I were to try and say, oh, I'm going to try and find a G2 and a G1. G2 and G1 would be part of the same curve, wouldn't they? So again, this would kind of like fail the vertical line test because this is the same curve. So we couldn't use the type 1. Whereas if we look at it sideways like this, our x value, left to right, is stuck between some function of y and then another function of y. So you have to be able to look at a region and determine if it's type 1 or type 2 by looking at the graphs of the curves. And then you pick which way to go. Is it possible to have both a type 1 and a type 2 region? Could you have a region that's both type 1 and 2? What about a rectangle? Is a rectangle type 1 and type 2? Yes, right? If I take a rectangle, I could say vertically that my y's are stuck between two constants, right? So I'd have a g1 and a g2. Or if I look at it this way, sideways, I could look at it, my x's are stuck between two constants. So a rectangle is both type 1 and type 2. For us, it'll be dependent on the problem. The problem will tell us whether or not, when we draw it, if it's going to have to be a type 1 or a type 2, or if we're free to choose either one. Notice, though, that in this drawing, our y is stuck between the constants, right? So we use c and d instead of a and b, all right? And our x's are stuck between two functions of y, because these are they're not functions of x, they're functions of y. And so we call it h1 and h2. So h2 is the one furthest to the right, h1 is the one furthest to the left. So the only difference is this changes your order of integration. Your constant's still on the outside integral, but now you're going with respect to y after you go with respect to x first. And if you do y'all see this is pretty much the same exact thing that we did before? If you want to find the volume between two surfaces, you would subtract the double integrals. Okay, so let's take a look at this one. And I will act like we don't have any picture for this. I think it's worth us working through it. So let's say we're asked to find the double integral over d of xy dA on the region bounded by y equals x minus 1 and y squared equals 2x plus 6. So we should just know by looking at this, y equals x minus 1 is a line, and y squared plus 2x plus 6 is a parabola that opens sideways, right? Yes? Parabola opens sideways. So if you have a parabola that opens sideways, you know that that's not a function of x. It's a function of y instead. Yes? So we should kind of see that. You could also say, if I try and solve this one for y, I have to take the square root on both sides, which means I'll have a plus or minus, and then again, technically, you won't have a function of x. So here's what I'll do. If we're going to try and do this as a type 2 region, we have to solve each of these equations for what variable? Get x by itself, right? So I'm going to isolate x. I'm going to say x is y plus 1. And then to get x over here by itself, we have what? 1/2 y squared minus 3. All right. I want to be fair to everyone. You're texting, right? I mean, that or you're punching away on a calculator. I'm not sure which one, but I kind of jumped on some people's cases at the end of class last time. For that, I know you weren't here, right? You weren't here? So I want to be fair to them. I don't accept that, right? Okay. Solve them for x, and now you can just try and draw them, right? So my question to you is, how comfortable are you with graphing these? It's a line and a parabola. Can you graph those? If you have trouble with it, you have your calculator, your graphing calculators, you can use that. You can go online and try and graph it, right? Wolfram Alpha, whatever. But you want to get comfortable graphing these by hand. These are pretty basic functions, or basic curves. How about the first one, y equals x minus 1? Looks something like this. How about the parabola? What could you do to get some points on this parabola? Plug in some values of x, like y, of y. So what if y is 0? What is x? So if y is 0, I'm at -3, which is back here, right? Y 0, x -3. What's another number I could plug in there? How about 2? What if y is 2? You get 4 here, 2, so you get -1, so you'd be at 2, you'd be at -1, something like that. What if I plug in -2 for y? Same thing, right? So I'd be at -1, somewhere in here. And so you draw your picture, and you can kind of see what's happening here, right? Now the question is, well, the question now should be, we already know this is type 2, right? Because we solved for x, not y. Question is, what are the restrictions on our y, and what are the restrictions on our x? So how about y? Our y values are stuck between two constants, right? Those constants come from where their points of intersection are. And then the x values are stuck between these two functions. Functions of y, not x. So shall we find their intersection? Okay, to find their intersection, set them equal to each other. And I'm going to set this one equal to this one. So I'm going to have y plus 1 equals 1/2 y squared plus -3. And what? Move things around here. 0 equals 1/2 y squared. I brought that y from the other side. I also subtracted 1. Y'all agree? I'll scale everything by 2, so multiply both sides by 2 just to get rid of the fractions. And then that factors to be y minus 4, y plus 2. And therefore, our two solutions are y is 4 and y is -2. That tells me my restriction on my y, right? From that. We're saying that at -2 right here, that's where that point is. And then this point up here hits up here at +4 and -2 for the y-axis. Okay, so let me write this down. Y is stuck between -2 and 4. My x is stuck between what and what? So if you're confused at all, remember the last problem, the top one was G2 and the bottom one was G1, right? Okay, just turn your head sideways and look at it that way. Okay, top one and bottom one. What's that? Or left, right, whichever way you want. Well, the one on the left is the lower and the one on the right's the upper limit of integration. No? Okay, let's see if we can just write down the double integral. Okay. -2 to 4. Okay, which one comes first? This parabola, which is this one, right? That would be our lower limit, right? And then the upper would be this line. So we'll have 1/2 y squared minus 3 on the bottom. And on the top, what is it? Y plus 1. And then what's the thing that we're integrating? xy, right? And then the order of integration, dx, dy. You can already tell that when we integrate this with respect to x, we'll have a polynomial, right? When we plug in this and this, we'll still have polynomials. We'll integrate that, we'll still have polynomials, and then we'll integrate. So it's all polynomial integration here, which is relatively simple compared to like techniques of integration that we might use for integrals, right? All right. I will show just the inner one. I'm not going to work it all out. I just want to, what's the antiderivative of xy with respect to x? half x squared y, right? And then we're going to evaluate that from what? X equals y plus 1, and x equals 1/2 y squared minus 3. I just wanted to do that because I wanted to show you again that I like to put what it is we're replacing. I'm going to replace the x with this, and I'm going to replace the x here with that. That'll be even more useful when we're doing triple integrals where we'll have x, y, and z. And so you want to keep track of what variables getting replaced with what. Okay, I'm not going to take it any further. You could go the rest of the way with that. Okay. I should mention that on your test for the final, a lot of the integrals that you'll be required to do, a lot of the problems you'll be required to do, it will be set up the integrals only. You won't actually have to evaluate the integrals because it'll take way too long. I mean, that would take you another 5 minutes, maybe, 5-10 minutes, who knows. And on a test, we don't really want to waste time doing integration, right? So there will be a lot of things like that. All right, next thing. All right, find the volume of the tetrahedron bounded by blah, 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 blah. All right, let's take a look at this. This one's somewhat interesting. So all I give you is this equation, or these sets of equations here. Find the volume of the tetrahedron bounded by these. So what is this right here? In three-dimensional space, what is this? A plane, right? What's the normal vector? What is the direction of the, or not direction, but what is 1, 2, 1, right? Okay, so that's a plane. What is this? In three-dimensional space, what is that? That's in 2. It's still a plane in three-dimensional space, right? But your z is not there, which means z is free. So that line, if you imagine drawing that line in two-dimensional space and then extending the z any way you want, then you get basically a plane that cuts through that line in two-dimensional space. What is x equals 0? The yz plane, right? And z equals 0 is the xy plane. So you have the xy plane, the yz plane, you have this other plane, and then you have this other plane. They all come together to form a tetrahedron. And we want the volume of that tetrahedron, right? So let's see if we can figure out a way of representing this as a double integral. So can we look at let's look at the region on the ground in the xy plane that would be below this tetrahedron. How could we find that? X equals 0 is what? I'm trying to look at all these. X is 0 is the ground, right? Isn't that what I'm looking at right here? If I label this X and label this Y, that's the ground, right? That's, I'm sorry, Z equals 0 is what I meant to say. Z equals 0. X equals 0 would be where here? So if I'm looking from the top, it would be this plane, right? And I'm looking from the top, so it looks like a line to me. And then what about X equals 2Y? Well, that would be the same as Y is half of X. So that's a line that has a slope of 1/2. So maybe it looks something like this. And again, I'm looking from the top down. So I've got this plane like that. Y'all agree? So I've got the ground, Z is 0. I've got X is 0. I've got this X is 2Y as I look down on it. Right now, have I enclosed a region on the ground yet? Do I have an enclosed region? No, right? I have a couple of regions, like I've got, this one here, but it's infinite, and this one's infinite over here, and so I have several regions, but it's not closed yet. So what about that last equation right here? Can I do anything with that? Yeah, z is 0 because we're looking on the ground, aren't we? So if I replace z equals 0 here, won't I get x plus 2y equals 2? So move everything over, divide everything by 2, negative 1/2 x plus 1. Y'all agree with that? And so that's a line, isn't it? I mean, now, of course, z has been flattened down, right? But that'll look like a line in the two-dimensional space here. And it has a y-intercept of 1 and a slope of negative 1/2, which means down 1 over 2, something like that, right? Do y'all see this? Agree with this? Any issues? Okay, so I'm going to graph that down 1 over 2 like that. Have I enclosed a region yet? Where? The little triangle? No? Right here then. That one, right? That's the only one that's enclosed by all three of those, right? Well, 4 because the bottom, the floor itself. So this is it right here. Now let me label some things here. This one was y is 1/2 x, right? This one was, what the hell was that? That was the plane that we squashed down to we let z be 0. So when we let z be 0, it was this one, wasn't it? I'll just put an arrow. That's that right there. Y'all agree with that? Is that a type 1 or a type 2 region? Type 1 or type 2? It's actually both, but one is better than the other here. Look, let's go with type 2 first, because that one's a little more complicated. If it's type 2, would you agree that the y values are stuck between two constants? Yes? But as I try and look at the x values, if I look in here, the x value is stuck between that line and then this line, right? But when I get to about right there at that point, now I switch to a different line, don't I? So you would have to look at that as being two separate type 2 regions. Two different ones. So you'd have to set up two separate double integrals if you look at it type 2. But if we go type 1, my x is bounded between two values, right? And my y's are always stuck between the same two. Well, yeah, this one is always the same throughout the whole thing, and then this one's always the same. So my G1 and G2 will be the same throughout. Make sense? So it's a good type 1. What point do I still need to figure out, though? I mean, like I can pretty much look at this and tell you what the smallest value of x would be, right? 0? But where do I stop? Where they intersect. Now, it looks like 1, doesn't it? But my drawing is pretty shitty, and I don't trust that drawing as being 1. So how would I figure out? Set them equal. When you say them, what you mean is, oh, yeah, this right here, right? Set that equal to this right here. Because those are the two lines I'm talking about, right? So let's find that point real quick. Verify that its x is 1. The intersection is when is negative 1/2 x plus 1 equal 1/2 x. If we add half x to both sides, we get it right away, don't we? Okay, so now I know my x is restricted between what two values? 0 and 1. My y is stuck between two functions of x. So my G1 and my G2. Which one was G1? This one right here. That's G1. And G2 is the one that was on top. So it's that one there. So 1/2 x and negative 1/2 x plus 1. We're almost there. Now, I have a double integral. We're going to go 0 to 1. we're going to go 1/2 x to negative 1/2 x plus 1. But what is the integrand? We haven't really talked about that, have we? What is it? What's the thing above this that we're trying to find the volume below? So I think this is where Mathematica would come in. Here's our region on the ground, right? Okay, looking at it from the top. One of the walls, see, this is a tetrahedron. One of the walls right here was created by that plane. Was it y equals 2x, or x is 2y? Or y equals 1/2 x? That's that wall, right? Z was free, so it goes up and down forever. And then another wall from that tetrahedron was this wall right here. That wall was created by what? X is 0, right? The YZ plane. And then the bottom of the tetrahedron, the bottom side, was what? Z is 0. But that top part right here is what? The plane. The plane, when we say the plane, they were all planes, but the non-trivial plane, right? The x plus 2y plus z equals 2. So how can you look at that plane as a surface? What do you have to do? Solve it for z. If you solve that equation for z, right, come up here. If you solve this equation for z, then won't you have a function of x and y? And that will be what your integrand is. So solve that for z, and let's throw that into the integral here. What do you get? 2 minus x minus 2y. And then order of integration, we go dy dx. Does all that make sense? And then dot, dot, dot. You could figure that out. Now, you may argue that there's an easier way to find the volume of a tetrahedron, you know, other geometric approaches, but that's just to show you how you could do it with double integral. All right? No questions? Yes? For what? We would have to know that that plane was up there? Is that what you're asking? Like, how would we know that? Or I'm trying to think of how I can explain that you would have to know that. All the other planes, right? One of them's the xy plane. Okay, that's the ground. So you know that the ground, z equals 0, is going to be, you're going to be looking from something all the way down to that, right? The other two planes were basically like vertical, so that couldn't be those. It would have to be that third one that has, think of the normal vector on that one has some direction to it, which means your plane is doing something, right? It's not like this. It's not perpendicular to the xy plane. So you would have to know that, yes. You could draw it. You could plug in some values and you know, get 3 points and draw the plane itself to know where it is. Does that kind of answer your question? Okay. Okay, order might matter. So take a look at that problem. Find the integral from 0 to 1, integral from x to 1, sine y squared dy dx. Now, I have it all drawn out here, but again, act like you did not have that, right? Just sit there and say, I gave you this problem. And I say, find this. This is a pretty important concept here. Right now, the way I have this written, can you tell me what type region I am using here? Type 1 or type 2? What's the outer integral? Outer integral is x, right? Inner integral is y. So this should be a type 1, right? We can tell that by the order of integration. So I'm going to like reverse engineer the picture from the integral. So from that, do I know my restrictions on x and y? Well, restrictions on x are 0 to 1, right? And then restrictions on y are what? X to 1. And I forgot to tell you the most important thing here. Shit, sorry. Why didn't I just go evaluate this integral? Why didn't I just go do it? Because you were asked to find that, right? Why am I doing all this over here? Anybody know the antiderivative of sine y squared? Anyone know how to even attack that? When in doubt, Wolfram alpha, right? So I'm going to ask it to integrate sine x squared. Okay? Find a general antiderivative of sine x squared. It's square root pi over 2 capital S of square root pi over 2x. What the hell's capital S? It's a Frenzel function. Integral. It's an integral that can't be done with any technique that we have. So we have other approximations. Like, you remember how hopefully in Cal 2 you saw that you can pretty much integrate almost anything if you can write it out in a power series and integrate term by term and get an approximation. Yes, that was like kind of the major point of power series. So this is, if it has a certain look to it, okay, if that series has a certain look, then it falls into a certain category, and this is the category Frenzel S integral, all right? In other words, we can't do it by hand, all right? Can't do it. So that's why I said, let's reverse engineer this region and take a look at it, because we can't do that by hand. Well, yeah, what does this look like, okay? Remember, this is G1, this is G2, right? Those are, X is restricted between two constants. So if I draw that, my X is between 0 and 1, okay? My Y, my region, the top of my region is just 1, isn't it? Which is constant. So it looks like this. Here's 1. So the upper bound is just constant 1 like that. That's G2. And G1 is X, right? Y equals X, which is the diagonal. That looks like this. Correct? That's G1. And then with X being 0, it created this triangle right here. Right? That's what it was. So someone could have phrased the question, you know, find the volume under f of xy equals sine y squared. And then they could have said bounded by the region, or the region bounded by what? Y equals 1, y equals x, and x equals 0. Like, that could have been given to us, right? If someone gave us this, we would have drawn this picture, right? So you see how we've gone from the double integral backwards to this? And the reason why is because it's the way that that integral was written was a type 1 integral. But can we look at it as a type 2? Yes. And that's what we would like to do right now. If we look at it like a type 2, this way instead, are my x values stuck between two functions? Are my x's between two functions? Looking sideways, yes? And then my y values are stuck between two constants. So let's try and change it up into a type 2. My y would be bounded between what? 0 and 1. And my x value would be between, so what you have to do is you have to take this line right here, which was y equals x, right? And you have to solve it for x, but it's already solved for x. So I would say that my x is between 0 and y. Does everyone agree with that? And now set up your double integral, but this time the order is different in the integration. So you have integral from, 0 to 1, then integral from 0 to y, and then you have still sine y squared, but this time dx dy, right? dx dy. If I integrate sine y squared with respect to x first, then sine y squared is a constant, right? So the antiderivative of sine y squared with respect to x would be x sine y squared, or sine y squared x. And that is going to be that's something at least I can do. So this will be equal to, here's my outer integral, and then my inner one here, we said that will be x sine y squared, and I'm going to evaluate that from x equals 0 to x equals y. And then I come back in, I'll do dy at the end. If we plug in y for x, what do we get? Y sine y squared. If we plug in 0 for x, we get 0, so that goes away. So all this turns out to be is integral from 0 to 1 of y sine y squared dy. And why is this integral better than the one that we had up there? You just do a u substitution, right? There's u and there's du, but you're off by a scalar. That's okay. So this is a very simple integration to do. In fact, if I put that in to Wolfram alpha instead, integrate, I'm using x instead of y, it's going to laugh at me that I came here to do that, right? That's it right there. Just negative 1/2 cosine. In this case, it would be y squared, right? That'd be it. So it'd be much easier to attack. And then you plug in your limits of integration and you're done. So the moral of the story is what? What's the moral of the story? Yeah, if you have a double integral that you look at and you go, what the hell? There's no way I'm going to be able to integrate that. Then try and identify what type of region it is. And maybe if it's a type 1, you can convert it to a type 2. And maybe that'll make the integration possible. So the order matters. During normal semesters, we usually try as a faculty to give every, like in a Cal 3 class, we'll have like 1 or 2 problems on the final that's common to all classes. And one of the problems that we've used in the past is one like this, where it says integrate, evaluate this double integral, and it's impossible to do unless you change the order of integration. So it's a very common problem that we give. All right, next, some properties of double integrals. If capital D is the union of 2 separate regions, D1, D2, then the double integral over the whole thing is equal to the double integral of D over D1 plus the double integral over D2. Does that make sense geometrically? You just take your region, break it up in 2 pieces, then all you have to do is find those individually, add the 2 answers together. Okay, double integral as the area of D. This is one of our main results. If you have that your function, your integrand, the thing you're integrating, is the constant 1, then the double integral over D of 1 will be equal to the area of D. All right? This only happens if you're integrating 1. How do we find areas in Cal 1? Cal 1. If I say, hey, look, everyone, in Cal 1, or wait, was it Cal 2? Depends on when you saw it. If I say, like, look between here and here, and I want to find the area underneath here, right? It was just a single integral, right? And let's say I call that D, the area of that. Then you would set up what? Integral a to b. If this right here is f of x, then we'd say f of x dx. That would give you the area under that. What I just said is that you can find the area of that region using a double integral. So what we do instead is look at that in three-dimensional space. So here's x, here's y. Here's that region, that same region on the ground, okay? A, B. Y'all see that? That's that region laying down on the side there. Except I'm finding the volume under a surface, right? But what did I say that that surface had to be? 1, right? So imagine coming up here and just going 1 unit up the constant 1 function, right? Do y'all see that? It would create that, right? And the volume is kind of like length times width times height, but what's your height? 1, always 1, right? So isn't that just really length times width? And that really just gives you the area. Do y'all follow that? It only works if you put 1 up here, constant 1. That's why they said the beginning of that note says that. If your function is just the 1, just the constant 1, then doing the double integral over that constant 1 will give you the area of the region you're integrating over. It's a nice little result. Okay, let me see if I can't bring this up here. How many of these do I have? Let me make sure this is the right problem here. It doesn't look right. I tell you what, I'm just going to do some problems that are in the book. I'm going to do a couple of these. All right. Find volume enclosed by the paraboloid z equals x squared plus 3y squared, x equals 0, y equals 1, y equals x, z equals 0. All right, what does that paraboloid look like? Well, it looks like a paraboloid, right? Paraboloids look like bowls, right? This one would go starting out at the origin, right? 0, 0, and it would go up. So I'm going to do just a real quick rough draft sketch of what I've got going on here. Got a paraboloid. Oh. Got a paraboloid. Looks something like that. And then what's x equals 0? Well, yz plane, right? So let me see. X, y, this is z. The yz plane. So basically that would cut that paraboloid in half, wouldn't it? I'm talking about like the back wall here. Extends both directions forever, everywhere. So I've cut that paraboloid in half. Y equals 1. Y equals 1 looks like what? It's plane. So it'd be like something like this. And it would actually go through here, right? It would cut through there. And it would be a plane that would look something like this. This is going to start looking like a disaster pretty quick, but I'm just trying to get an idea of where everything is. Y is equal to X. It'll be a plane. It cuts through diagonally on the ground like this. I'm not going to draw the plane because it's just going to look like a mess. Z equals 0, XY plane. So let me try a two-dimensional picture over here. X is 0 was this, right? That's X is 0. Y is 1 would be this. Y is X would be this. Z is 0 is the ground, isn't it? So do I have a region that I can integrate over? In here, right? That's our enclosed region. The question is, what's the surface down to that we're looking for here? It's the paraboloid, right? The paraboloid is a function of two variables. So remember, our paraboloid comes out at us, right? Comes up towards us like a bowl. And we're saying if you just look at that, the stuff underneath that bowl. So here's my bowl, right? Coming down like this. Underneath that bowl, down on top of this, what's the volume of that? Make sense? Type 1 or type 2? Either one, right? I'm going to go with type 1. Is the intersection point obvious here? Yes? Okay. What's the restriction on X? 0 to 1. Restriction on Y? The bottom is what? X, and then the top is fixed at 1. So X to 1. So I can set up my double integral, 0 to 1, X to 1. And then now what is the thing on top? We said was the paraboloid, which had that formula x squared plus 3y squared. And then what was on the bottom? What was keeping us making that forming the solid on the bottom? The xy plane, which is z is 0, right? So I don't really need to account for it in here. And then this is dy dx. And then you're off to the races with that. What do y'all think? You can handle that? Okay. Let me tell you what you can do here for homework out of this. Is there a homework set at the end of that or not? No? Okay. So for homework, for 12.2, if you look at page 707, we'll do number 7, 15, 17, and then 21. This is a lot. 21 through 29 odd are good problems just to get used to interpreting the word problem and like drawing things out. Like it's kind of like what we just did, that last problem. And then 37, 39. Oh, wait, hold on. Those are, no, scratch that. 43, 45. Those two problems are where you reverse the order of integration. Okay. That's it. Now, we're going to move on to the next section, which is 12.3. So for 12.3, can we turn off that other light? Not because I don't want to put people to sleep, but it's really hard for me to see the screen from the side like that. We'll let a little more light in. Okay? Is the glare too bad over there? You all right? All right, so far we've established double integrals for the regions shown here. We've got over a rectangle, over type 1 and type 2. But now we need to look at, some other regions that don't fall into any of these categories. And so we have to do a little reminder of polar coordinates. How many of you have seen polar coordinates? Okay. Polar coordinates, it's just a different coordinate system, right? Cartesian, when you say XY Cartesian, everything is, you have two axes that are perpendicular, your X and your Y axes. You say, hey, look, if I want to get to some point in two-dimensional space, give me the point, 2, 3. I'll walk out along the X-axis 2, then I'll walk parallel to the Y-axis up 3, and I'll be at a point, right? But that's not the only way to get to that point. You could have said, instead of walking out and going up, you could have said just turn a certain angle and then walk a certain distance, and you'd also get to that point. And that's what polar coordinates are. So if you rotate by some angle, right? Rotate by some angle, like start off here. Say, okay, let's say I want to get to that point right there, right? I just have to turn until I'm pointing it at it, and then walk out a certain distance. You see, oh man, oops. There, trying to get there now. My radius was maxed out. You get the idea though, right? I turn a certain distance, I walk out a certain distance, and I will be at that point. So r and theta instead of x and y. Theta angle, r is distance out, radius. But if you look at it that way, then this forms a right triangle, and of course in a right triangle there's all sorts of relationships, and what we can do is we can establish these relationships right here. So x squared plus y squared is r squared, comes from the Pythagorean identity, right? Since it's a right triangle. X is r cosine theta, comes from the definition of cosine. Y is r sine theta, it comes from the definition of sine. And then arctangent of y over x is equal to theta, comes from, again, the relationship of tangent to our sides. If we do it that way, then this xy up here can be written r cosine theta, r sine theta. All right, now, a rectangular region in polar coordinates. So we've always said rectangular regions in Cartesian coordinates look like rectangles, right? Our standard idea of a rectangle. So our x is between two constants, our y is between two constants, and that draws this, a rectangle in Cartesian coordinates. But there is also a rectangle in polar coordinates, but it doesn't look like a rectangle. Still called a rectangle, but in a different coordinate system. So what would happen if I said, hey, look, show me all the points that are given by r and theta where your theta is between two constants and your radius is between two constants? What would that draw? It would draw something like this. So look, here's my radius, okay? I'm going to fix my radius between two constants. Do you agree that all the points on this curve right here have the same radius? And all the points on the outer arc here have the same radius? And all these points in between, the radius of those points are between those two, right? And then my angle here, that everything along this edge, right, has the same angle. To get to those points, I have to turn the same angle. And every point on this edge, I have to turn the same angle to get to those. And every point in between, the angle is between those two angles. So that's what a rectangular polar region looks like. Your theta is between two constants, and your radius is between two constants. That's not what we normally think of when we say rectangle, is it? We don't think of drawing something like that. So if someone says, hey, draw me a rectangle, you could be a real smart ass and be like, well, what coordinate system would you like me to be in, right? Would you like a polar rectangle, or would you like Cartesian rectangle? Because you could draw that, and that would be a rectangle. Now, is that a type 1 or type 2 from what we did the previous section? Could you even look at that as a type 1, type 2? I mean, I don't know, it's kind of hard to see it that way. Let me do it this way. Let me drag that theta out a little bit more. How about that? You could maybe do something like this. You could maybe turn that into 3 type 1s, right? Like this would be type 1. You have a curve on top, curve on bottom. X's are stuck between 2 constants. Curve on bottom, curve on top. X between 2 constants. Same thing there. But it would be pretty ugly because you would have to figure out what this curve is, right? It's part of a circle. You have to figure out what these lines are. Now that would take a little work also. But why do that when we can just convert our whole system over to polar instead of Cartesian? So just look at the vast variety of regions we can have. I mean, it is possible for me to integrate over that. That means if there's a surface above that, I can find the volume just down below that. Above this, right, down to the XY plane. And that's definitely a region that you couldn't handle before. Or if I go all the way around like that, come back like that, I could integrate over that washer. Could you convert that into type 1, type 2? Yes, again, but you would have to break this up into separate regions again. Okay, double integrals. All right, I'm going to see if I can't get this to come out here. Do you have little keyboards on your printout too? You do? Last semester, I finally figured out how to disable that feature where the little keyboard didn't pop up all the time. But when I made that document, it was popping up, and I wouldn't realize it, and I would accidentally copy it. Okay, remember with Cartesian that the dA, right, that little thing right there, dA, meant the infinitesimal area. And the infinitesimal area came from this picture, right? We cut up our region into little rectangles. We said it had an infinitesimal width of dx. It had an infinitesimal height of dy, and then the area of that thing is just those two multiplied. Yeah? But look at polar. If we're going to do converting everything into polar coordinates, and we're going to try and do a double integral over some rectangle in polar coordinates, we will still have to integrate a function, but that function, all the x's and y's will have to be converted to r's and thetas, and our dA will not be the same picture. Our infinitesimal area on the ground is no longer a standard rectangle. So the question is, how can we approximate the area of this thing? So here's how we do it. And I'm going to put this on the board to see if y'all remember this. Do y'all remember that if you have a slice of pizza like this, and if this is theta, and this is the radius, then the arc length, the length of this arc, this is a pre-cal formula. The length of that arc, S, is equal to r theta. The one condition we have is that theta must be in radians for this formula to work. All right? And one application of this formula is if you were to ask someone, what is the circumference of a circle? So if I have a circle with radius r, and I want to know the length all the way around it, right? Then what's the angle here? 2 pi. So the length all the way around it will be the radius, which I'll just call r, times the angle, which is 2 pi. And so the circumference is 2 pi r. Yes? But this is the more general formula. So with that in mind, I want you to look at my picture here. We are going to draw this little red thing. We are going to let theta change infinitesimally. So this little thing right here, that little angle is d theta, an infinitesimal change. So that's like the theta is here. And then the radius, we go out a certain distance for radius, and then we let that radius change a little bit so we get a dr, our differential in radius, which gives us some thickness to that slice out there, right? And so if I want to know what is an approximation of this red region, it would be approximately this dr times whatever this is, because that's approximately a rectangle, isn't it? What's this length? This arc, it's r d theta. Where does that come from? This formula right here, r, but remember that was d theta. So this formula is r d theta. And that gives us this piece. Do y'all follow that? Okay, so when we look at this dA in polar coordinates, it doesn't just convert to dr d theta, it's actually r dr d theta. Right? I only yelled it because that's what people are going to forget. Okay? Someone is going to forget. Who wants to volunteer? Any volunteers? Thank you. Okay. Forget that R. It's all going to be wrong after that. So it's kind of a give and take. You have some problem. If you want to go to polar coordinates, fine. You convert all your x's and y's over to things with r's and thetas and everything. You set up your double integral. Everything's fine. But you must introduce an r into the integral, into the integrand. If you forget the r, it's wrong. Now, later on, in a further chapter, we are going to talk about, this is a geometric way of trying to explain where it comes from, but we will actually have a mechanical way of determining where that r comes from. And then we'll use that to be able to not only go from Cartesian to polar, but we can change our Cartesian to any other variable. It's called change of variables. So to do that, when you do a change of variables, like if you want to go from xy to r theta, if you want to do that change, we have to introduce an r. What if we want to go from xy to some other coordinate system? What is going to appear in here? And we'll have a formula for it. But that's beyond where we are right now. Okay, so here it is. If we are given a polar rectangle, r and theta are between two constants, then the integral of the function of xy dA converted over, notice that I just take the function f, I replace x with what? Well, what's x in polar? R cosine theta. What's y in polar? R sine theta. All right? Then the dA here becomes r d theta dr. And these restrictions, notice that the theta is between two constants. We call them alpha and beta. And the radius is stuck between two constants. We call it a and b, right? Alpha and beta is a and b in Greek, right? But we just we like to use Greek letters for angles, right? So theta, alpha, and beta. And then r is stuck between a and b. Notice the r in the formula. What else do I want to point out there? Is there anything else? Oh, let me ask you. Do you think, once you've converted everything over, do you think the order of integration matters here? Do you think you can switch the dr d theta if you switch the two things over there? Yes. Because now that you convert over, we're basically back to Cartesian. It's just a double integral. All right, so the properties of double integrals will hold. When the region is not rectangular, we can't do that. So let's look at this. Find the volume under this bounded by that thing there. So again, let's try and act like we don't have the picture. The picture kind of makes things a little bit too easy. All right, so we have z equals 3x plus 4y squared. The region that we have is the one bounded by x squared plus y squared is 1, and x squared plus y squared is 4. And we say with y is greater than or equal to 0. So let's work on the region first. Let's try and draw it. X squared plus y squared is 1. Is? X squared plus y squared is 1. Is? Circle. Radius. 1. Okay. All right, so draw your circle radius 1 in here. Then x squared plus y squared is 4. So radius is 2. And it's the region bounded by those two. So we do have a region, right? But I threw one more condition in here. Y had to be greater than or equal to 0, which means we can't be below the x-axis, which means we want to cut off that bottom piece. Right, scratch this down here. So we just want that right there. Now, does everybody look at that and go, definitely looks like a polar region, right? Like you don't look at that and go, type 1, type 2, right? You look at that and think, okay, I've got a radius stuck between two things and I've got an angle stuck between two things, right? So give me a restriction on my theta and give me a restriction on my radius if I'm going to go to polar here. 0 to pi, that's my angle. And then what about my radius? 1 to 2. 1 to 2. All right. So we pretty much have the region under control, don't we? We've got restrictions on theta and r. We're trying to find the volume underneath that thing. So that function up there is already solved for z. Solved for z, so I can look at that as f of x, y is this. Now, in order to be able to convert completely over to polar, I have to replace all my x's with what? R cosine theta, and all my y's with r sine theta. So if I switch this function over to r theta, it's now going to be 3r cosine theta plus 4, and then I need to square y, so that would be r squared sine squared y. Everyone okay with that? Yeah, I don't know why I have y. I'm glad you're not okay with that. Multiply by what? You said you were going to forget it.
Oh, I didn't know. I just said volunteer. I was like,
I meant who was going to volunteer to forget it on the test. That's all right. You can still forget it on the test. I'll let you. Okay. So I'm going to go double integral, right? Let's do our theta first. We're going to go from where to where? 0 to pi. Our r will be 1 to 2. Now our function, which is going to be 3r cosine theta plus 4r squared sine squared theta, but then all of that times, and this is where we have to remember the conversion, right? All of that times r d what, d what? dr d theta. Now again, I could have made it d theta dr, but I would have had to have switched these two around over here. So that r is going to have to distribute through, won't it? Before you do your integration. So, just do you see, if you forget that r, it's pretty much game over at that point as far as getting the correct answer. So I would have integral 0 to pi, integral 1 to 2, 3r squared cosine theta, plus 4r cubed sine squared theta, and then dr d theta. Tell me if you agree with this, the next line I write. Integral 0 to pi 3 r squared dr times integral 1 to 2 cosine theta d theta plus 4 integral r cubed, let's see, shit, hold on, got these backwards. 1 to 2, 0 to pi, 4r cubed, 1 to 2, dr times integral 0 to pi sine squared theta d theta. Do you agree with that? Why? I mean, why can I do this? What is it? A couple of things happening here. First of all, there's a plus sign between these two, right? So I can split it completely into two separate double integrals. And then this one right here, let's imagine that this was the only piece. The two variables we have, right, r and theta, are completely separated from each other by multiplication. Remember that property we had? That was a very special case that if we could separate x and y, then we could separate into two integrals. Do I need to go back and bring up the note or not? No, you can look at your notes. I have r and theta separated. If and only if that's, the case, you can then take that and split it into two separate regular integrals. So I took the 3r squared, did that. I took the cosine theta, did that. I'm going to multiply those two answers. Then over here I have the plus, and I did the same thing on the other one, here and here. You don't have to do it that way. You could just go through and integrate, but I just wanted to point out that that is possible. Now, could you integrate r squared? Pretty easily, right? 1/3 r cubed. Plug in, get a number. Antiderivative cosine? Sine? That's pretty easy. Antiderivative r cubed? Pretty easy. Antiderivative of sine squared? How would you do that one? Just do a trig identity, right? Trig identity, you can, like a power reducing formula, right? Power reducing, you can rewrite that as 1/2 minus 1/2 cosine 2 theta, and then integrate term by term. So, if not, go back and look at Cal 2. How do we do, trig integrals? I guess my point is all of those can be done fairly easy. All right, what do you think? Nice? I'm stopping there. I'm not doing more of that. So the next one, here's the picture, just FYI. We had the surface here. We had our region on the ground. We were going to find the volume of that solid right there. It's kind of a cool looking shape, isn't it? So that's what that double integral would yield. So find the volume of the paraboloid, blah, 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 and the xy, bounded by the paraboloid in the xy plane. So on this one, you're given z equals 4 minus x squared minus y squared, and then you're given the xy plane. This goes back to a little bit what we talked about earlier, like how am I going to know what it looks like type thing. So this is a paraboloid, right? It opens which way? And how can you tell? So if this is x, this is y, this is z, that's a paraboloid, so we know it looks like a bowl. If I plug in 0, 0 for x and y, where am I? 4? What if I plug in 2 for x and 0 for y? Where am I? Right there. What if I plug in 2 for y and 0 for x? Won't I be here? Follow? What if I plug in negative 2 for x? I'd still be here, and 0 for y, sorry. What I'm trying to get you to see is that you should be able to determine that this paraboloid, opens down. Bad picture. Okay? That's what's happening. It's opening down. Now you could tell by the negative x squared and negative y squared that it opens down. It's like a parabola. The negative coefficients give you the downward. Now, by looking at that, I want the volume of the solid formed by that paraboloid and then the xy plane, which is the ground z equals 0. So if I look at where the paraboloid hits the ground, it creates a region on the ground, doesn't it? Like a shadow. And so that shadow looks like what on the ground? This will be my R. It's a circle. What's the radius of the circle? 2. Now, you could again get that by doing what? Come back up to the equation. How could I tell that this is going to give me on the ground a circle radius 2? Set z to 0, then you're on the ground, and then move things around, you get x squared plus y squared is 4, which means that x, your radius is 2. So I already know that this is going to be my region on the ground, everything in here. And that is a perfectly suited polar coordinate, right? Rectangular polar region. If so, what's my restriction on theta? What's my restriction on r? Okay, 0, 2 pi, and 0 to 2. Agree with that? So if I start at 0, and I start rotating through the whole thing, and while I'm rotating, I'm allowed to go from 0 to 2, right? I will draw the whole region. Can somebody give me another way of drawing it without using the same restrictions? Use something different. Okay. Something other than that. Sorry. Okay, let me try and force your hand then. How about, can you do it if you only go from 0 to pi? What's that? Careful. Don't get caught up in symmetry here. Our region is symmetric, isn't it? Our region is symmetric. Is the surface above it symmetric? In this problem it is, but in general it's not, right? So in this problem you could just go to like the first octet and grab that and find the volume above that and multiply by 4. But what I'm saying is the surface above this particular circle is only symmetric because it's a paraboloid. If it's not, you can't just take one octet. Did I say octet? Quadrant. No, I'm trying to get you to draw that circle if I tell you can only have a theta go between 0 and pi. What are you going to have to do then? So check this out. Let's say that I'm pointed out. I'm going to draw a dotted line pointing in the direction. Okay, that's like pi over 4, right? If I say I'm pointing at pi over 4 and I walk out between 0 and 2, I will draw everything on that little line, right? And if I rotate a little more and I'm pointed this way, right, 0 to 2, I'll draw everything over here. And if I go all the way to pi, I can draw everything up in the top half of the circle, but I haven't done the bottom half. It's kind of a stretch here, but how about this? Negative 2 to 2. Now, radius doesn't make sense to be negative, right? Doesn't really make sense for radius to be negative. But remember, the idea was that you're going to turn a certain angle and walk out a certain distance, right? Well, I could say, look, if I want to get back there, I could say turn this angle and then walk backwards. If you do this, you will draw the same. You will draw the whole circle. Because when I point out this direction, right, I will walk out 2, but I will be able to walk backwards 2. So I would draw everything here. And if I rotate a little bit more, I will draw everything there. And rotate a little more, everything there. And then eventually, when I go only to pi, I will have drawn everything. Right? Does that make sense? But you could not change this 0 to 2 pi and negative 2 to 2, because then what would happen? You draw it twice. See the difference? And you don't want to overlap, because that'll give you an incorrect answer. Y'all there? Okay. All right. So let me ask you something here. I'm going to stray from the notes a little bit. Actually, this may even come up later in the notes. Find formula for area of circle, radius r. And let's make it capital R so we don't mix it up with things. Everyone here knows the formula for the area of a circle, right? Area is pi r squared. Now, remember that what we said in the previous section is that if you do a double integral over d of 1 dA, what does that give you? If you do a double integral of 1, it gives you the area of d, doesn't it? This gives you the area of d, doesn't it? So let me draw what I'm trying to find the area of right now. It's a circle radius r, right? Can somebody tell me what, if I look at that as a region on the ground in polar coordinates, how could I draw that region in polar coordinates? What would be my theta? What would be my r? What would be the restrictions? And let's just stick with 0, 2 pi. That other thing I showed you was just a kind of an FYI thing. 0, 2 pi, and then radius is what? 0 to capital R, right? Everyone agrees that would draw this? Now I'm going to use a double integral to get the volume above that, but what I'm going to use is 1, right? So I'm going to have double integral, 0 to 2 pi, 0 to capital R of 1, right? R dr d theta. So I had to include the r because of the polar. And now, let's just do the integration right here. Can you do the antiderivative of r with respect to r? Half r squared, right? So this is going to be 1/2 r squared, and I'm going to replace r with what? 0 and capital R, right? And then that's going to be integral 0 to 2 pi d theta. So when I plug that in, what do I get? Capital R squared 1/2, right? So now I'm at integral 0 to 2 pi of 1/2 capital R squared d theta. And now integrate this with respect to theta. This is a constant, isn't it? So the antiderivative constant, that would just give me, I'll put it over here, 1/2 capital R squared theta, and I'm evaluating from where? 0 to 2 pi, plug in 2 pi, and what do you get? Half of 2 pi, but half 2 pi is just pi, so you get pi, right? Capital R squared, and then when you plug in 0, you get 0, and so that's it. That's kind of a proof of why the area of a circle is pi r squared, using a double integral to prove it. Now, in Cal 2, you can do it with a single integral, but you have to, well, if you don't convert over to polar, you could do it in polar integral, you could do a polar integral, or you could do a regular old integral x and y, but then you have to look at the circle as being like part of a square root function. And so later on, we'll see we can do the same thing to verify formulas for like volumes of spheres and things like that. And, all right, just wanted to show you that. Next on the list. So look at this. If we have a surface and then a surface underneath it, and we want to find the volume between them, and it's on top, their shadow on the ground is a polar rectangle, then all we have to do is subtract the two double integrals, just like we had before. This is a good one. Find the volume of the solid below x squared plus y squared plus z squared equals 1. What is that? A sphere. So the volume below a sphere and above this cone. So you have a sphere. Inside of it is a cone. That cone is centered at the origin, right? Because check it out, 0, 0, 0 is on that cone. And it opens upward. So you have a cone and then a sphere. And where they close off some volume, some solid, we want to know that volume. Got it? What does it look like? Snow cone, right? Snow cone, right? What's the volume of that snow cone? Everyone understand geometrically? So don't we have like a top function, which is the sphere, and then we have a bottom function, which is the cone. So we're going to want to take the sphere on top, double integral of that, and subtract double integral of the one on the bottom. The question is, what is the region that we're integrating over? So how do you find the region you're integrating over? Geometrically, we have to look at it straight from the top down, right? From the top down, what is that region? It's a circle, right? Which is perfect for polar coordinates. But the question is, what is the equation of that circle? Because it's where the sphere hits the cone, right? That's where you would, if you imagine where the sphere hits the cone, cutting everything else off the picture, where they hit each other, that's a ring that goes down to the ground. So how can I figure out what the equation is of that circle? Set the two surfaces equal to each other, right? The surfaces, where the surfaces hit each other. So let me write down the two surfaces we have, x squared plus y squared plus z squared equals 1, and z equals square root x squared plus y squared. So we first had to know a little bit about what this picture is. I mean, we couldn't just like start swinging at it without having any idea. We have to realize the sphere, we have to realize the cone coming out from inside, up, hitting it at a circle, and then that circle we can find by setting these equal to each other. Well, what I'm going to do is I'm going to take this z right here and I'm going to plug it in right there. Okay? And when I do that, I square it, so it becomes x squared plus y squared plus x squared plus y squared equals 1, right? And now put those together, we get 2x squared plus 2y squared equals 1. Divide everything by 2, x squared plus y squared equals 1/2. And this is my radius squared, is 1/2. So what's my radius? 1 over root 2, right? Or root 2 over 2. Everyone agree with that? And we don't have to look at the negative, right? So what I need to draw is a circle that has a radius of root 2 over 2, and it's everything in here. So it's important that you understand that if you're standing on this thing, right, and you're looking up to the cone where the cone hits a sphere, right, this is like the shadow. Like if the projector was the light, right, this would be like the shadow down on the ground. And the shadow of their that solid would be your region of integration. Do y'all see it or not? Yeah. All right, so give me some restrictions on theta and r here. Zero, 2 pi. 0. Yep. And now we have to talk about what the hell it is we're integrating, right? So I have double integral 0 to 2 pi, 0 to root 2 over 2. We'll take a break after this problem, okay? Now, I need to understand that there is an upper and a lower function that I am going to subtract. And then I will have out here, when I'm done with that, r, right, because I don't want to forget r, dr d theta. Did I get that right? Yeah, dr d theta. Okay, so instead of looking at from the sphere all the way down, right, we're looking sphere and then cone. So top one is sphere. So I need to somehow rewrite this right here is my sphere. Solve for z, right? Take your sphere equation, solve it for z, but then do what? Change it to polar, right? Okay, so I'm going to come back up here. I want to take this right here. If you solve that for z, you would get this. Z equals square root 1 minus x squared minus y squared. Do y'all agree? See how much, I don't have any more room down there. The other one's already solved for z, isn't it? All right. How would I go about changing that to polar? Replacing my x squared with what? R cosine theta, and replacing my y with r sine theta, right? But I think it's easier if you realize that this is really just square root of 1 minus x squared plus y squared. So I factored out a negative 1 there. Now why did I do that? Because what's x squared plus y squared in polar coordinates? In polar coordinates, it's r squared. So anytime you see x squared plus y squared, you always can convert that over to r squared. So this just becomes in polar square root of 1 minus r squared. And then this one up here changes into square root of what? Well, what's x squared plus y squared? R squared. Square root of r squared is just r, right? Assuming that r is positive, which it is. So that means my top function, which was the sphere, turned into this, but then converting to polar turned into this. And then my bottom function, which was this cone, converting to polar just turns into r. So I put in here, what, square root of 1 minus r squared, and then over here, r. Follow? Sphere goes on top, or goes before the cone, because the sphere is on top of the cone. And then let me distribute the r through there. I'm just going to write down what this would be in here. It would be r square root 1 minus r squared minus r squared. That would be what you're going to integrate. And you're going to integrate that with respect to r, then with respect to theta. How would you integrate this first piece right here? U substitution, right? So basic, just 1 minus r squared would be u. That's kind of du, so that would be just basic substitution. That's power rule. Integrate, and you're off to the races. Okay? Questions? Break time? Let's come back at 3. All right, so I just passed out the next mini exam. I have this being due in a week, right? No? Week and a half? Next Wednesday, right? So a little bit of time on this, but You should try and finish it by Monday, because I think Monday I might give you the next one. So I put on here that you are allowed to work together, just to make sure it's formally written down so you have evidence of that. The first 3 problems are all Lagrange problems. But number 3, all I'm going to say about number 3 is that it's a Lagrange problem with 2 constraints. And I did not do one of those in class. I showed you the formula, and I think I said I wouldn't give you a test question on that, and I guess I meant an in-class test question, because I'm giving you take home. So if you read through the book, it has, you know, an example with 2 constraints, and I'd be happy to provide you with something if you came by or email me or something. I've got other stuff. I think in the spring I did do a problem with 2 constraints, so there is a video somewhere out there that has 2 constraint problem worked out. I could find out where it is and point you to it. Number 4, volume under a hemisphere above a tetrahedron. That's basically like we just did. We just did a sphere and a cone. This is a hemisphere, top part of a sphere, and then below that and above a tetrahedron. So you got to kind of, what you'll notice about that is the tetrahedron, I don't give you any information other than the vertices of the tetrahedron, which means there's a lot of work you have to do to come up with the equation of the whatever the hell it is that you're going to be integrating over. So enjoy. And then number 5, this one's interesting. I like to see what people do with this. Find the volume of the solid under this surface and above the xy plane, and over the region x greater than or equal to 1, y greater than or equal to 1. So what kind of region is that? 1 to infinity in both x and y, right? See what you do. Because, I mean, I've given you like a rectangle before, right? In Cartesian, you go from A to B, C to D. So just think about how this might be different. All right, number 6, I'm going to talk about that in a little while. I'm going to do something kind of like that. Not like this, but something we should discuss before I expect you to do number 6. Find the volume of a solid ball with radius 4, which has been drilled out with a drill bit of radius 1. The drill bit ran parallel to the z-axis and was always tangent to the z-axis. The center of the drill bit passed through the point 1, 0, 0. So it's not a sphere with the center drilled out. Or a ball with the center drilled out. It's a ball with the drill bit's been moved over a little bit and drilled out. And I want to know what the volume of the ball is now. And that's a little more involved. If it was just drill out the center, it would be a lot easier to do. Pardon me? They intentionally wanted the center of their drill bit to be offset. So they didn't want it to go through the center, which would make a difference in the volume, right? All right. Let me see if I've got this. Yeah. Nope. I'm going to see if I have a picture. That's your last mini exam right there. No, this one that I just opened. Where is it? I may not have the picture here. Flight 370, what the hell is that? Oh, I wrote some code to try and explain to my students why, you know how they were talking about that flight that disappeared being on those arcs? Remember that? Do you want to see it? We're here anyway, right? So apparently there was a satellite. That's the part of the Earth that the satellite can see, right? That's the only part it can see. And then if I move the satellite closer in, it can't see as much of the Earth. If I move it further away, it can see more, right? So we had some satellite sitting out there, and well, you know what? This may not be my final version, so it may not look good. Ping distance. Well, it's good enough. If there was an electronic signal sent from somewhere in this dark area to the satellite can measure the distance, then that means it would have to live somewhere on that green circle, right? And then, what else did I have here? Oh, yeah. But then the airplane itself took off from right here where my cursor is, and only had so much fuel on it, so it could only have traveled in this blue region somewhere, right? So to narrow down that entire green circle where it intersects the range of the plane would have to be somewhere on this arc or on this arc down here, somewhere in there. So that's why they were looking at arcs north and south. Anyway. But then I heard that all the data was screwed up anyway, so it didn't matter. But it was a fun exercise. What's that? Yeah, well, I think it was, that whole thing's a mess. Okay, 7. Let me see if I can find, let me just look one more place here. Well, I wanted to show you a picture, but I can't find it. A picture of the thing, the problem that you're asking me about. Let me just show you. Sphere or ball, right? This XY plane, XYZ axes. The drill bit came down and was always tangent, so it was always touching there, right? Has a radius of 1, which in the center of it went through 100, right? Here's the x-axis, so here's 1. There's the center of the bit, right? And the bit came down like this. Does that kind of make sense? No. So the drill bit was always, there's the z-axis, and it's always parallel to that, but it's always tangent to it, so it's touching it. So all right. Shall we continue? Where were we? 12.3, polar, we did that. Okay, so if we have, we did that. If we had type 1 regions in Cartesian, then we're also going to have type 1 regions in polar. Type 1 meaning, well, the regular rectangular region in polar was our two constants, our two variables are trapped between constants, right? R and theta. But what if our theta is trapped between two constants, but our radius is trapped between two functions of theta? So instead of our radius having to be on this arc and on this arc, that radius may vary depending on what the angle is. So do y'all see how this is like a type 1 Cartesian? So if you have a type 1 polar, where your theta is between alpha and beta, two constants, and your radius is between two functions of theta, h1 and h2, then your double integral, the order will matter now, right? Alpha to beta, and then h1 to h2. F is still going to be converted. There's my r. Don't forget your r there. Then dr d theta. I cannot switch that order. Here I was looking for the damn picture, and I have it in my notes. Fucking idiot. Sphere radius 3 has a cylinder of radius 1 drilled out of it, as shown below. Set up the double integral, which yields the volume of the remaining solid. Do not evaluate. There's your picture. There's your sphere offset, right? Drilled out. See it? I was going to say it looks like Star Wars stuff. I'm not a big Star Wars person, but that does remind me of Star Wars somehow. Death Star? Okay. No, seriously, it looks familiar. In fact, I need to see it because it's a childhood memory, but I can't put it together right now. Oh, let's just look. Sorry, I have to see it. Okay, yeah. See, yeah, it looks like that. It looks like that, kind of, but it's not drilled out all the way. That's a self-proclamation over there. That's well. All right. Okay, so how in the hell do we do this? Okay, no one has any ideas? Okay, so what we drilled out was a circle, right? Projected down to the XY plane. Okay, that's your region on the ground. Okay, and what do you want to know? What do you want to do with that? Okay, I think I'm with you. Do you know the volume of a sphere? Okay. Do you know the volume of this sphere? Well, it has a radius of 3. There's a formula for it, right? So you know the volume of the whole thing. If you could just find out the volume of what got drilled out, you subtract that from the volume of the sphere, and you know the volume of what's left, right? So the question is, what's the volume of what got drilled out? So coming back to this picture here, if I come in here and I take the sphere out, that's the part I drilled out, but it's not a cylinder. It's actually Mathematica is having some trouble. Come on, it doesn't want to turn that over. You can kind of see it. It's hard to see, but there's like a little piece of the sphere up there, like a little round part. So it's not just a cylinder. It's got a round, it's at an angle there. So would you agree that the volume of this part that got drilled out is everything below the sphere, right? But only over that circle. And then times 2, because we have one below also. Agreed? Everything below the sphere over that circle. Here's the challenge, though. I'm not going to do this problem because if it would just be giving you the test, the question. But let me show you something similar. Let's say that I had, let's say 1, 2, 1, 2. Let's say I had a circle on the ground like this. And this was X and this was Y. Is that a polar region? Is it a rectangular polar region? See, this is where things get a little bit tricky. Is it a rectangular polar region? Is your angle trapped between two constants? What constants? So look, how would I get to this point right here? Let's just say I picked this point here. I would have to turn a certain angle, right? And I would go a certain distance, right? So I would turn some angle and then walk out some distance. What if I wanted to get to the edge of that circle? Right there. I would turn that same angle and walk out to the edge of that circle, right? And if I want anything in between, I could vary my radius anywhere in between here, right? The problem, though, is that if I turn to a different angle, let's say I turn to this angle here, is the distance I walk out to get every point in between, is the distance the same as it was for the previous angle? It's changed now, right? That's right. Your radius is a function of theta. How far you walk out depends on how far you're turning. Now, what's the angle that I'm allowed to turn through? So 0 to pi. So like if I'm pointing out this direction, that means theta is 0. Do I have a certain radius? It's 0, right? Because I can only be at that one point where the circle touches tangent to the origin. So at theta 0, I'm at 0. And then if I turn just a little bit, right? If I turn just a little bit and point out like this, I have a pretty small variation in radius. And then as I turn more, it gets bigger, right? And as I come back, it gets smaller. And then where do I have to stop my angle? At pi, right? It does not make sense for me to go to like 3 pi over 2. Yes? So what I know right now is my theta is stuck between 0 and pi. Yes? Okay, what is the equation of that circle? What is it? No? How would you get it? Do you know the equation of that circle in Cartesian coordinates? Okay, what is that in Cartesian? And we would need this formula, x minus h squared plus y minus k squared equals r squared, right? That's a general equation of a circle centered at hk radius r. Where's our center? 0, 1. So I would plug in 0 here, so I get x squared plus, then what? Y minus 1 squared, and then equals 1. That's the equation in Cartesian. We can convert a Cartesian over to polar, right? Before I do that, I'm going to expand out. Is that correct? Multiplying this out. What's x squared plus y squared? In polar. R squared. R squared. Pardon? Oh, why did I get... Oh, sorry, I did that mentally. Thank you. That should be 1, right? I apologize. I got one step ahead of myself but forgot to cancel. This was 1 on this side. This 1 came off this. And then they're going to cancel, so it'll be a 0 on the other side. What is this in polar? 2r sine theta, right? And then I have equals 0. What am I trying to come up with? I'm trying to come up with r as a function of theta. So can you solve this for r? Well, let's factor an r out. Right? And then we have two possibilities here, right? R could be 0 or r could be 2 sine theta. And only this one makes sense, right? But we do have a smallest radius. The smallest radius it could be would be 0, right? You all following this? Okay. You said 2 sine theta, right? Is that just off of your knowledge of you've just been told that, or you've seen enough of the polar circle stuff? Okay. Yeah, depending on your familiarity with polar circles, polar equations, you may know what something looks, you may know what the polar equation is without needing to go through the whole set of steps. And if you're there, that's okay. All right, so that's it. So what I have now is back up here, I was doing my restriction on theta. Now what's my restriction on r? What's the restriction on R? We just got, right? We said the smallest that theta could, or R could be would be 0, right? And then the biggest, this is my H1 and this is my H2, okay? My two functions of theta. The smallest it can be, right? When I'm standing here and I'm looking out, what's the one that tells me how far I can go? That's my 2 sine theta, right? What's the one on the inside? Well, as I look around here, the smallest it can be is 0 the whole time, right? So it'll be 0 to 2 sine theta. Does that make sense? Now we go and set up the double integral. So you have your double integral. It will go from what? 0 to pi. The next one, 0 to sine theta. And then what's in the integrand? The top minus the bottom. Well, what was the top? The sphere. So you have to find the equation of the sphere. You have to solve it for z. You have to convert it to polar. And then minus 0, because we're going to look at the xy plane. And then remember, double that whole thing, right? Because we're taking 2 of those, the one on top and bottom. And what else do you have to put in the integral? R dr d theta. And then you're off to the races with that. Okay? So the tricky part of this problem is the conversion of the integral, of the region into polar. That's the hardest part, I think. Well, and then the integral itself might be pretty bad too, but as far as what we're trying to do in this class is just getting it converted over. All right. That's the end of 12.3. What shall we do? How about for homework on this? We have 5, 9, 11, 18, 20, 23. Sorry, that's page 713. Now, I will warn you that on 20, is very, very much like the problem that I just showed you with the drilled out thing, except they have the drill going through the center. But they don't give you, they give you the radius of the drill is R1, and they give you the radius of the sphere is R2. So they don't tell you the exact numerical values of the radius. So they want a general formula, basically. Say, hey, look, if you have a sphere radius R2, you drill out right through the center, a drill bit radius R1, what's the remaining volume? And your answer will be in terms of R1 and R2. So just a more general problem, but center of the sphere makes the problem much easier, right? So, all right, let's move on. 12.4. We're just grinding away today. Well, there's always going to be a give and take, because you would have to, everything gets shifted. You know, it's not just, so every variable in the problem, so other problems may present itself also. Plus any translation you do in the plane, if you stay in Cartesian, right? Are you saying just stay in Cartesian?
We can start in Cartesian, shift it left one, you know, 1 unit on X, 1 unit on Y, to the center, or whatever. Shift all your other variables in the problem by that, and then
that's right. So then all your equation of your sphere and everything else would change also. And I think you would still have the same challenge as far as the integration would be similarly difficult. But you could try it. You could just mess with it to see how it worked. Okay. Where are we? 12.4? Applications of double integrals. So we're going to do a couple of applications. We've already seen one application, and that's if you want to find the area of a region, you can do a double integral over 1, right? And then that'll give you the area of the region. But there are some other applications. Suppose we have a lamina. So lamina is a two-dimensional object. Now, in real life, we would consider a lamina to be like a sheet. And even though we all know that this is three-dimensional, right, it has some height to it, it's very small, we'll consider this a two-dimensional lamina. And so when this piece of paper was manufactured, they tried to make it so that the density of the paper was the same throughout the paper. Does that make sense? Like the mass per unit volume, how much paper is actually right here in this little point is the same as how much is here. But if we had the ability to measure accurately enough, we would realize that this has different density throughout the page, right? In fact, by me putting ink on it, laser, right, I've changed the density at certain places too. I mean, you would have to have a really fine instrument to measure that. But this, if it's all the same density, it's called a homogeneous lamina. If it's not the same density throughout, then it's non-homogeneous. And so we would like to know if there's a way that I could figure out where the center of mass of this is. You know, what's the density, what's the mass of this, first of all, and then what's the center of mass? So if I were to try and balance this on a point, there's like one point where it should balance, right? And that would be its center of mass. So if I know about its density at every point, can I tell you what the mass is and then where that balancing point is? That's where we're headed. So we've got this lamina, two-dimensional lamina. Suppose that the density, mass per unit area, is variable, meaning that the density at every point in the lamina may be different. Then the total mass of the lamina is the sum of the masses at infinitely many infinitesimal rectangles. Ugh. So it's like you just take the lamina, you cut it into an infinitesimal rectangle, and at that rectangle, you tell me what the mass is. And then you add all those up. Well, if the mass here, if you're given a density function, if density is mass divided by area, then if you multiply both sides by area, you get that the mass is density times area. The density is a function you have to be given, and the area we already know we got from dx dy. So that means that to figure out the mass of the whole lamina, you need to do a double integral over the region of the density times the area, or density times the infinitesimal area, add them up. Okay, so the only thing that's changed in this whole thing is that instead of using f of xy, we're using rho of xy, and rho of xy is what we call a density function. Now, why would we care about finding the mass of a lamina? Well, let's talk about that in a minute. Another application, suppose we have a lamina, same thing, but instead of having the density at every point on the lamina, we have some electrical charge. So if we were given a what's called a charge density function, sigma xy, so we know the charge density at every point on the lamina, then if we add them all up, right, over the whole lamina, then we get the total charge on the lamina. So again, it's a double integral. There's our charge density function, and there's our area our differential area. Right? Same picture though. So what I want you to see it as is all of these problems, even though they may have some physical meaning, to us the way that we first started looking at double integrals, it's still a region and then a height of a function above it, and we're looking at finding the volume below it, right? That's what it is. It's just that what does that height represent? Well, if it's just the height, then we're talking about the volume under a solid. If that height is a density, the density of mass density, then it's going to represent the total mass of this thing down here. If that's the charge density, then it's going to give you the total charge down there. So whatever that is, depends on what class you're in, right? Depends on what you're studying. But it's all the same double integral. All right. Now, I'm going to do this example, but let's see where this is headed. Moments about an axis. Suppose we have a lamina in the xy plane, so we have another lamina. The moment of the lamina about the x-axis is this. So it's capital M sub x. It's that same density function, but all we've done is we've tacked a y on the outside. And then if we want to have the moment about the y-axis, it's that same density function, but we tack an x on it. And what is the moment? This is a physics terminology. Moment of a particle is the mass times its directed distance from an axis. So if you have a lamina, right, and I pick some point right here, the moment at that point is the mass times the directed distance to an axis. So the moment about the x-axis, right, the moment about the x-axis at that point would be the mass, which is density times area, times the distance from here to here. What's the distance from here to here? Well, that's your y-coordinate, isn't it? So that's why we multiplied by y. When we were looking about the moment about the x-axis, we multiplied that rho by y. It's because y is our distance here. And if we want the moment about the y-axis, then the distance to that point is now x, so that's why we multiply by x. So we'll use those formulas. But then from that, using those two formulas, we can find the center of mass. And so the center of mass of a lamina is going to be this. It's the moment about the y-axis, which is the formula from before, divided by its own mass. So these are two separate double integrals, right? The moment about the y-axis is this double integral, and then you divide it by its mass, but the mass was a double integral, wasn't it? So in order to find the x bar, which is the x-coordinate of the center of mass, you have to find two double integrals. And then you find the y-coordinate of the center of mass by doing this, which is, again, two integrals. But you already know what mass is. So to find the center of mass of a lamina, you'll have to do three double integrals. Moment about x, moment about y, and the mass, and then put them all together. So why is it that we would want to find, if we had a two-dimensional lamina, why is it that we would want to find its mass and center of mass? Why would that be? What's one reason why we might like to do that? Like in physics, when you're studying things, like, do you usually, like if you're studying like the way that certain objects move, do you get into all the technicalities of the weird shape of the object, or like in basic beginning physics, or do you just look at it as a point? Like a point mass, right? So you say, okay, here's a point, and it has a mass. Well, what you're really doing is you're taking something that may have a complicated shape, and you're just looking at as you find its mass of the whole thing, and then you find its center of mass, and then you can consider the whole object as just a point with a certain mass. And then it simplifies. You take all that other crap out. Now, if we're throwing something through the air and it's spinning and it has, like a tennis ball versus a baseball, right? I mean, there's very complicated physics going on there, right? You can't look at those as point masses if you want to know the way it's going to behave, right? The laces on the baseball affect the way the wind, as it travels through the air, how, you know what I'm saying? Versus I mean, it depends on how complicated you want to get. Does anyone remember the first equation you ever saw for objects falling on Earth? Like, there was a formula for the distance an object is off the ground if you drop it from a certain height. It's like d of t equals negative 16t squared plus v naught t plus d naught. It's like a general formula that you get in the very beginning of a physics class. And it's but the biggest thing on that formula is they say, this is the formula if you, what? Take out air in a vacuum, right? Well, we don't live in a vacuum, so what the hell is the use of that? Well, you have to start somewhere, right? And then from there, then you put air in, and then you put in the coefficient of static friction when you're trying to drag something across the desk. And the physics, the equations become more complicated, right? But you don't want to walk in, trying to introduce someone to physical, dynamic systems and be like, all right, we've got a coefficient of static friction, about all these different things that affect things. It would be overwhelming. You have to start basic and move from there. So a center of mass and finding the mass is a way that we can take a complicated situation, make it very simple, work with that, and then as time goes on, we add the different crazy stuff in. Rotational inertia, all those things. Yeah. How many of you have taken some physics? Yeah, I mean, you know what I'm talking about, right? You start off with point masses, and then you move from there. Now, right now we're doing a center of mass of just a lamina, but imagine we're going to be able to extend this out to 3 dimensions, so we'll be able to find the center of mass of a 3-dimensional object and its moments about the x, y, and z axes, and so, I mean, it extends. Now, moment of inertia is a different formula that we have. It's basically the same as the moment, but it's the square of the distance. Square of the distance. How would that change your moment versus your moment of inertia? What can you tell me about y squared and x squared? What will it always be? Positive, right? It'll always be positive. So the moment of inertia takes away which side of the axis you're on. So you don't have to, it won't affect it with a negative sign. Does that make sense? Like if I'm doing a moment around the x-axis, if I'm up above it, then that's going to be a positive, right? Moment about the x. That would be positive. If it's below, it would be negative. But with moment of inertia, it squares it so it doesn't matter. Now the moment of inertia of a particle is its mass times its square distance from directed distance from an axis. What's moment of inertia? Rotation, right? Yeah, it's like if I were to take this lamina and it had a certain density throughout, and I were to try and like rotate it about the x-axis, like what is its resistance to that? Or if I were to try and rotate it around the y-axis, like what would its resistance to that be, right? That's what your moment of inertia. Like spinning it, yes. Either way, you can look at it both ways. Right? Okay, well, should we do some computations or do y'all want to do computations? Let's start off, let's go right to a center of mass problem. How about that? Because the center of mass, we'll have to find the moments, and then we'll have to find the mass and everything else. So this problem will kind of knock them all out at one time. Sound fair? What are we supposed to get through today? Oh, shit. Seriously? Okay, so let's pass this around. Sign in, please. I'd like to spend as little time here in this section as possible, honestly. Because this is just set up the integral, and then from there, it's everything we've talked about. So let's do this one. So find the center of mass of the region bounded by x is 0, y is x, 2x plus y equals 6, and its density function is given as rho xy equals x squared. So let me look at our region on the ground. X is 0 is the y-axis, right? Y equals x is the diagonal. And then 2x plus y equals 6. That's a line, right? So y equals negative 2x plus 6. That has a y-intercept up here at 6. And slope negative 2. I don't know, it does something like this. Y'all agree? I mean, this is a very rough sketch, but that's what we would have. Looks like we have this region right there. Where do they hit each other? 2? So you just set them equal to each other, right? So I set this equal to this. So x equal to negative 2x plus 6, which gives me 3x is 6. I didn't not believe you. I just wanted to make sure I had that documented. 2. So x is 2, right? So all I need to do is do a double integral over this region, and I'm integrating. Yeah. What's that? 2x is what? This right here? What? I'm trying to figure out where these two lines hit each other, right? So I solve this for y, solve this for y, and set them equal to each other, right? So I'm doing their intersection here. Oh, that's all right. That gave me this. Now, why did I need 2? Because this is a type what region? Type 1 region. So I'm doing double integral over a type 1 region. I need the limitations or restrictions on x, and then my y is trapped between 2 functions, g1 and g2, right? So x is between 1 and, 0 and 2. Y is between what? What's the bottom one there? The bottom one is x, right? Top one is negative 2x plus 6. Right. Is everyone comfortable with the idea that that's definitely not a polar region? Like I shouldn't be trying to go polar here? And the function up here, rho of xy, that right there, that's like my f of xy, right? So what do we need for center of mass? For center of mass, we need to compute x bar. X bar is defined to be the moment about what? Y divided by the mass, right? That's what x bar is. I'm referring to your note here, note 12.4.3. Now, each of those are 2 separate integrals, so let's go ahead and figure out what those are. And I'll start with mass. That's just the x component of the center of mass. The mass is defined to be the double integral over d of just your rho of xy, dA, which for us will be the integral from 0 to 2 from x to negative 2x plus 6. And then what are we integrating? The density function, which is x squared, and we're going dy dx. Everyone have that? Well, on your take-home, you have to do them. Yeah. On the take-home test, let me see. Number 7, I say find the center of mass. So it's very similar to the problem we're doing right now. On the final, no, I would just have you set them up. Yeah. Yeah, because this becomes very tedious. But this should give me a numerical value, all right? So let's see. Does Wolfram alpha do double integrals? Well, you wouldn't have to, right? You could do this. Integral, then what? X squared from, what is it going from? X to negative 2x plus 6. See what it does. Okay. Now, can I take that? Does it let me grab that? It doesn't, does it? They've kind of put some restrictions on Wolfram Alpha. You used to be able to do a lot more with it. Now you have to pay to do more. They got you. They got you. Okay, was that it right there? Right? Whoa. Was that it? I don't trust it. That was it? Okay, so let me try and integrate that. From 0 to 2. 52. I'm trusting that I didn't screw up that first one, but I'm just showing you that's a way you could check to see if your stuff's working out right. All right, so that's the mass, right? That's the mass. Okay, so now what we would do, so I'm going to put here maybe 52. And then we would want to get the moment about y. And the only difference in moment about y is that we put what here? X rho xy, which means my double integral is 0 to 2, x to negative 2x plus 6. But now instead of x squared, it'll be x times x squared. So x cubed, dy dx. So the big difference is that right there. Then you go grind that one out, right? Shall we? We'll integrate x cubed from x to negative 2x plus 6. Now watch, I believe that Wolfram Alpha is smart enough to do this. Integrate parentheses, and now inside that I'm going to integrate, but I want to do that from 0 to 2. Let's see if it can interpret that or not. Let's see what it does. No, it didn't have it. I don't know. Do you think it'll? Yeah. You know what? Let's take that one out. Let's go back to that first one while I'm here. The first one was x squared, right? I don't use Wolfram Alpha. I use Mathematica. So dy, is that what you're saying? From x to negative 2x plus 6? Yeah, that makes more sense. Let's see if it does it. Right, because we integrate with respect to y first. And then from there, we take that and integrate that. See if it'll let me grab this. Copy plain text. Okay, yeah, good. I can copy this here. Maybe it won't let me just copy that. Okay, and then now I want to integrate that dx from 0 to 2. Four. That's a little different than 52, isn't it? Look, the only reason I'm doing this is just to show you that there are ways that you can use this tool to check your work. I mean, by hand on your take home, I expect you to do it by hand. It'll be a little grindy, but you know, get one or two of those under your belt, you'll feel better about yourself. Okay? All right, so we set that up, we've carried that out the rest of the way. Now, when we get those two answers, right, we take this one and we divide it by this one, and that's our x bar. And now you have to find y bar. To find y bar, the only thing we're going to need is what? Moment about x. That's the only difference. So I don't have to do mass again. So a moment about x is double integral over d, but this time it'll be y times your x squared, dy dx. Dot, dot, dot. Do you all feel like you could handle that? What about the one on your take home? Number 7. Find the center of mass of the following lamina if the density at any given point in D is given by that density function. I would definitely consider, you should consider polar coordinate conversion on that one, right? Because your region is a good polar region, right? I would not stick with Cartesian. So. All right, we're going to move to 12.5. All right, well, if we had double integrals, we can now have triple integrals, right? And if we had a rectangular region with double integrals, right, the bottom, the ground was, x was between two constants, y was between two constants, then something similar to that with a triple integral would be x is, well, we have to first kind of take our heads out of where we've been. Our domain has always been on the ground, right? And then we've had some surface hovering above. And we've been talking about volume under that surface. But we've needed 2 dimensions for our domain, and we've needed that 3rd dimension for the surface, and then the volume made sense. Now, a triple integral, your domain is 3-dimensional. And your surface lives in a 4th dimension, which we can't see, right? So now we can't really talk about volume under the surface because we don't have like a shadow to project anything onto. Does that make sense? So when we were talking about in double integral, we were talking about domain being the rectangle on the ground. Now, if our domain is 3-dimensional, what is a rectangle in 3 dimensions really going to be? It's going to be like a box, and that's what we have here. So if we have a triple integral, we have this box E, which is going to be our x is between 2 constants, y is between 2 constants, z is between 2 constants, and we just have this nice little box, right? But what I'd like for you to notice is that with this box in 3-dimensional space, the shadow of this box on the ground is what? Is a 2-dimensional thing, and that's a rectangle in 2D, right? So the shadow of this box is a rectangle. Yes? That's the way we're going to attack triple integrals. We're going to look at the domain, which is 3-dimensional. We're going to try and look at its shadow, which is 2-dimensional. And we're going to look at its shadow and say, is that type 1, type 2, is it polar? What's the deal with that? Right here, its shadow is rectangle, right? So if we have a box, though, then the triple integral is just going to be 3 integrals, right? Triple integral over E of some function of 3 variables, which again lives in 4-dimensional space, so we can't see it. And it'll just be these 3 integrals. Those are our limits of integration. There's our function, dz, dy, dx. And do you think the order matters? Not on a box. Not on a box. You can swing things around. Now, how many different variations are there? 6 variations? You could have dz dy dx, dz dx dy, dy dz dx, dy dx dz, dx dy dz, dx dz dy. So there's 6, right? What if you had a quadruple integral over some hyperbox, which was 4 variables between constants? Then how many different variations of the quadruple integral could you have? So how is that computation happening? How did this become 6 starting with 2? Yeah, this is all just counting principles. So, all right. Shall we? We have to start off somewhere. X squared yz. Triple. All right, what I'm going to do is I'm going to just write out before I write, I should probably point out with this notation where you have the closed interval, cross closed interval, cross closed interval. I talked to you before, that's not cross product, right? If they don't tell you which is which variable, it's always assumed x, y, z. That's always the assumption here. So this is your x interval, y interval, z interval. So that means if I set up this triple, it's on a box, which means it doesn't matter which order I go in here. I'm going to go 0, 2, I'm going to go 1, 2, I'm going to go 0, 1, and then what am I integrating? Well, x squared, y squared, z, d what? dv. Wait, that's different now, right? Triple integral, we have dv. What was it before? Double integral, it was dA, because dA was the infinitesimal area. dv is now the infinitesimal volume. What would it be if we had a quadruple integral? D whatever, right? Whatever you want to define it, but it would be the like a hypervolume, which would be just length times width times height times that fourth thing. That would be your hypervolume. You can get a little weird once it gets out of something you can connect to visually. It gets strange. All right, so we've got that. I should replace dv with what? D. The order here matters. D. If I'm reading from left to right, z, y, x, right? Because wasn't the x 0 to 2, the y was 1 to 2, and the z was 0 to 1. So it goes from the inside out. So you would be working, if you were to work this integral, you would do this one first, which means you would integrate x squared yz, treating what like what? Like x squared y is a constant, z is your variable. Integrate that and then replace. So I'd like to work through that. Let me do it that other way that was suggested. Why don't we do the inner integral first? Okay, the inner integral is integral from 0 to 1, x squared yz dz. Okay, the antiderivative of that will be 1/2 x squared yz squared. So I just did power rule on z squared. Or is that power rule on z? And got 1/2 z squared. And now I'm going to evaluate that from where to where? 0 to 1. What's 0? What's 1? Z0, Z1. Plug in, what do you have? Z is 1, you just get 1/2 x squared y. Plug in 0, you get 0. So this is the first inner integral. Now that's going to get plugged in. So the next integral, which will be my middle integral, will be integral from 1 to 2 of what we just got, right? 1/2 x squared y. What's my middle integral with respect to? Y. What's the antiderivative of that with respect to y? So it'll be 1/4 x squared y squared. Evaluating from It's y, right? So we're going to replace our y with 1 and 2, 2 to 1. I plug in 2 for y. What do you get when you plug in 2 for y? X squared. When you plug in 1 for y, and I'm subtracting this, 1/4 x squared. And that gives you 3/4 x squared. And now you move on to the outer and last integral. Which was integral from 0 to 2 of just 3/4 x squared dx, which gives you 1/4 x cubed, right? Evaluated from 0 to 2. You could say x is 0, x is 2, but at this point we're at the last integral, so there's only one variable left. Plug in 2, you get what? 2, and then plug in 0, you get 0, so the answer is 2. Any questions? The main thing I wanted to see you to see there is just, again, keeping track of what's being replaced with what. The fact that you could go inner, then middle, then outer, instead of trying to do it all at the same time. Okay, so how about triple integral over region E, where the shadow cast on the xy plane is a type 1 region? So look, what I've got is I've got some solid, right, E. This is my domain. The domain is the solid there, right? That's the thing I'm trying to integrate over. And then I take a shadow straight down onto the xy plane, and when I look at that shadow, it's type 1. Does everyone see it's type 1? If I turn it this way, you might be able to see a little better. In fact, if I take this thing completely out of here, look at it from the top, spin it around like that, right? That's type 1. My x is between two constants. My y is between two functions of x. So it looks something like this, right? Now, here's the difference, though. My solid is bounded up and down. The top and the bottom are bounded by two surfaces. So I'm going to take the middle of that solid out. So if you look at it this way, your x's are stuck between two constants, right? Our y's are stuck our y values are stuck between, right, x is between two constants, y is stuck between two functions of x, g1 and g2, yes? But then, when you take that region and plug it in to get that solid, that is stuck between two surfaces. Those surfaces we'll call u1 of xy, I have to use xy because it's a surface, u2 of xy. So those two surfaces are my top and bottom of the solid, yes? Okay. If that's the case, then your integral will look like this. So if your a is between two constants, your y is between two functions of x, your z, up and down, is between two surfaces, u1 and u2, then your triple integral sets up this way. Notice the outer integral, right, with respect to x has the constant. Then you go to the middle integral is with respect to y, it has your restriction on y. And then your inner integral is your z, and that's your two surfaces you're stuck between. And of course, you have your function in there. So what about this one? Evaluate the triple integral over E of y dv, where E is bounded by those planes. Okay, let's try this one out. 0, 0, 0, 2x, 2y. Trying to do triple integral over E of y dv. So let's try and draw E first, if we can. X is 0, YZ plane. Y is 0, XZ plane. Z is 0, XY plane. So that's pretty much like cutting three-dimensional space into the different octants, right? That's all of our like coordinate planes that we've had before. But we also have this one right here. So let me try this. Draw a three-dimensional picture here. I think I'll do a different. I'll go with X this way. I don't do this one enough. Y that way. That's still right-hand rule, right? I can do that. What? Where? I don't know what you're talking about. Yeah, that's some other rule. What is this right here? It's a plane, right? Can you peel me off 3 points on that plane real quick so I can draw it? So 2, 0, 0, right? So just let y and z be 0. Solve for x. So if y and z are 0, the x is 2. Let's grab the axis points. Those are the easiest to get. How about x is 0, z is 0? What's y? 2. And then if 0, 0, 4, so 1, 2, 3, 4 up here, right? That would be enough for me to draw, connecting those together, that plane right there, right? That's kind of the plane. And then if I have the ground, right? The ground is z is 0, the bottom of this. And then the xz plane was y is 0. That's this side. And then this back side like that would be, it's a tetrahedron, right? Okay, so the back side there would be x is 0. So we've got this tetrahedron, which is this three-dimensional solid, yeah? What is the shadow of that tetrahedron on the ground? That triangle on the ground, right? It's this thing down here. So what I'd like to do is call that thing on the ground D and draw that in a two-dimensional picture. X, Y. Where does it hit on the y-axis? 2. Where does it hit on the x-axis? 2. And draw a straight line. All right, so that's my D. I should draw it the same color here. What type region is D? Type 1 or type 2, but type 1 works out pretty good here, right? If I look at that as type 1, x is between where and where? 0 to 2. Y is between 0 and... Yeah, we can get this one by just looking, right? How would you get it with not looking? Where did this line come from? Where that plane hits, right? So you would take the plane equation we had and let z be 0, and you would have the equation. But I can just tell by looking at this, the slope is -1, and the y-intercept is 2, right? So 2 minus x or negative x plus 2. Doesn't matter how you write it. And now, because it's a triple integral, what I need to do is figure out what's the restriction on my z. So look at this tetrahedron. That shadow was cast down, right? What is the top and what is the bottom? So what I'm going to do is, do we all agree that this right here is the top and the bottom is right under there, right? The floor. The top is the plane, isn't it? Solve for z. What's the plane solved for z? Four minus 2x minus 2y. So this is 4 minus 2x minus 2y. And we can call that u2xy. And then over here, the u1xy is what? Z equals 0. It's the floor. Do y'all see how that connects to the picture from before? Most importantly, the top and bottom surfaces. For us, the top surface was the plane, right? The bottom surface was z equals 0. And then the shadow on the ground turned out to be type 1. For us, it was just a triangle. But this is the generalization of everything. Okay, so that means that my z is between where and where? I'm going to continue this right here. Z is between 0 and 4 minus 2x minus 2y. And what is it that I'm trying to find the triple integral of? So back up here, the triple integral of y, right? dv. So everything I've done up to this point is just to give me my limits of integration. Then I have to integrate y, and then have all my variables in the correct order. So here I go. Integral 0, 2. Integral 0, 2 minus x. Integral 0 to 4 minus 2x minus 2y. Okay, what am I integrating? Y. With respect to what first? dz. With respect to dy, so dx. Okay, so first thing you would do is you would integrate y with respect to z. What's the antiderivative of y with respect to z? yz. Then you replace z with this and this. And then you take that, integrate that with respect to y. After you do that, you replace it with y with 2 minus x and 0. And then you go with respect to x and one last time. You get the idea, though? I mean, I'm not going to carry through the integration on this. All right, well, if the shadow on the ground is type 1, well, then it would make perfect sense that the shadow on the ground could also be type 2, right? All right, so what if you have some solid you look at the ground, your y's are between two constants, your x values are between two functions. So looking at it from the top, it looks like that, right? That's what it looks like. Our y values are between two constants. Our x values are between two functions, h1, y1, h1y, h2y. So we've done this before, right? Double integral. But the only difference is now we have this z part of it. So our z is still going to be some top surface, which we'll call u of xy, u1 of xy, and u2 of xy, top and bottom. How does it change the integral? What's the only difference? This is pretty much the same setup, right? But your y and x's have changed places, basically. Your y is stuck between the constants. Your x is between the two functions of y. So therefore, in the integral, that's going to have to change also. Your order of integration is going to be different, right? You're going to have the outer integral is going to be with y, and then x is the next one, then z is the inside. Okay? This presents somewhat of an issue. I'm not going to do that one. Think about this. The solid that you have in three-dimensional space, everything I've done so far, I've said take that solid and project the shadow down onto the XY plane, right? And then look at that and say, is that type 1 or type 2? But why not take that solid and project it over to the XZ plane instead? Right? Take the shadow and shine it to the side. Now, do I do this? Yeah, like that. What if you had a solid that went this way? Can you all see that solid? Look at its shadow. Look at its shadow on the what is that? This is X. That's on the YZ plane. This is on the Y. If I project that onto the YZ plane, doesn't that look like a type 1 region over there? But all these things change because, look, take this out. Pretty much, yeah. Look, if I show you the labels, because this is the YZ plane, right? The YZ plane, your Y is stuck between two constants. Your Z is stuck between two functions of what? Y. And then your surface is stuck between what? They're surfaces, and those surfaces are functions of what? Of both Y and Z. So when I bring those in, that surface right there, to get this surface, you have to know what Y and Z are, and then it spits a point out an X value. And then this one right here, same thing, give me a Y and Z, and I'll spit that one out. Now, I'm not going to give you any of these, but it just goes to show you that you could projecting the shadow down is what we will mostly do. But you could project it onto one of the planes or onto the other plane, and then you could have type 1 on the, when you project it that way, it could be type 1, it could be type 2, it could be polar. We haven't even looked at polar when you go shadow down yet, right? So that's just to give us some appreciation of how many different ways it can happen. I'm not going to do this where I project it onto different planes. Okay, let's look at this one. We're getting close to the end. This will be our last problem for today. All right, let's try and set this up quickly. We have triple integral of z dv. E is the solid bounded by the cylinder y squared plus z squared equals 9. The planes x equals 0, y equals 3x, z equals 0 in the first octant. Okay, find this triple integral. Now let's try and get our head around what the hell this solid looks like, okay? What is y squared plus z squared equals 9? Cylinder, which way does it go? Runs along the x-axis. What's its radius? 3. So it's like 1, 2, 3. I've got the cylinder, rough sketch, coming down the x-axis like this, right? If this is my x-axis. This is my y, and that's my z. So I've got this cylinder coming down the x-axis. All right. X is 0 is the YZ plane. So it's like the back of that cylinder. Y is equal to 3x. That's a plane, isn't it? Y is equal to 3x. So how would I draw that? It'd be tough to draw, right? This was 3, right? Y equals 3x would mean... Yeah, it'll be kind of like an angle like this, and it's a plane like that. Okay? I'm just trying to get an idea of what's going on here, right? That plane's going to cut the cylinder. In fact, it'll cut it, and it'll look like this. Now, I'm not expecting you to draw it, but I mean, that's what's happening. I'm creating this slice through the cylinder. That slice created this wall. I still have the cylinder, which creates that wall. The back wall is being created by what? X is 0, and then Z is 0 is going to be the bottom. Do y'all see that picture? Now, that might be difficult to see, so maybe you just try and go to the 2D picture first. Tell me what's on the ground. Well, X is 0 is this. Y equals 3X, 1, 2, 3, over 1, so that's Y is 3X. Z is 0 is the ground, so that's where I am. How can I figure out how to close this region off? If I'm on the ground, I can use this one and say what? Z is 0, so Y squared is 9, which means Y is plus or minus 3, but I'm in the first octant, so I don't have to consider negative. So Y is 3, so that's going to be right here. That's Y is 3. And can everyone see that this triangle is that triangle down there? Yes? So that shadow on the ground is type 1. And this right here looks like I have like a top surface, which is the cylinder, right? And then a bottom surface, which is what? So what's this top surface right here? What's my U2 of XY? Pardon me? How do I get that surface? Solve for Z, and what do you get? Square root of 9 minus Y squared. Right? So all you did was took this and solve for Z. That goes here, right? Because this cylinder is a surface, right? It is a function of X and Y, isn't it? Isn't this a function of X and Y? But X is free. Agreed? X is free because we were allowed to move down as far as 1. The only thing that needs to be under control is the Y coordinate or the Z needs to be controlled by the Y. What about the U1? That's that bottom piece, right? That's when Z is 0. So U1XY equals 0. Well, I hope that makes sense. I know this picture might be a little bit tough to kind of sketch out, but so can we set up the triple? All right. So what are my limits of integration here? That'll be the inner one, right? So let me start from the outside in. The outside is the restriction on X, right? Which is what? We never got it, but it's 0 to 1, right? 0 to 1. Then the inside, or the middle, would be my restriction on Y. That's because it's type 1. 3x to 3. And then my inner integral is my restrictions on Z. 0 to square root 9 minus Y squared. And then finally, what the hell am I integrating? Z, right? D, Z dy dx. And then you could go from there. we can see that there's another integral possible. We could have cast that shadow on a different plane, but since I'm not asking you to do that, don't worry about it. This is one thing I did want to say, application. If the double integral of 1 over, with respect to area, is the area of the d from earlier, then the triple integral over E of 1 dV is the volume of the solid. Isn't that the problem we just did? Is that the problem we just did? It appears twice in the notes? Kind of weird. Is that the exact same problem? Oh, find the volume. Okay. Yeah, so if we were to find the volume, right, it's the same cylinder, same lines. The only difference would be what? At this point right here, where I put Z, you would put what? 1. Damn. All the way through 12.5, or 12, whatever the hell that was. We're on track. Everyone sign in? Okay, have a good day.